That would be by Souvik Das. Sorry if I pronounced that totally wrong.
No,
So
you're right.
maybe, perfect.
Hmm?
Exactly. Could you share your slides?
Sure. How do I? Jesus. Oh, share screen. Okay, got it. Just have to. Okay. Now, can you still see it?
Yes, we can see the slides. Perfect.
Okay,
So please
perfect.
go ahead.
All right, let's get started. So I have 20 minutes or 25-ish, I'm assuming. So, okay, so let me
I was
start.
just looking, sorry if I'm being muted. I was just looking. Yeah, you have I would say 25 minutes maximum. So if you're between 20 25 is perfect.
Okay, 20-ish. Okay. All right. So let me introduce a new topic that we've been working on. So this is, we're trying to use a quantum computer that works with annealing to try and solve problems in high energy physics. So for this talk, we're going to show you our work with track clustering for primary vertexing. So the team who has worked with me mostly they were undergraduate students at the time. Many of us they've joined back for their PhD with us. So Andrew Wildridge was an undergraduate. He's a PhD student now. Sachin is a PhD student. Andy Young is of course a professor, and I'm with Purdue. Souvik, staff here. Okay, so quick outline of the talk. We're going to discuss what proton-proton collisions of the LHC are and what we do when we say primary vertexing at CMS. I think there was already a session in the morning that dealt with primary vertexing, so we're probably familiar with it, but nevertheless, since this is an independent talk, I will introduce it. I will introduce quantum annealing itself, the theory, and the hardware that is available with the D-Wave company in Canada. I'm going to describe primary vertexing as formulated for the quantum annealer. We're going to show the performance of the D-Wave machine on one event, and then I'm going to show our formulation of benchmarking against a classical simulated annealer. Then we're going to show off the comparison between quantum annealing results versus simulated annealing results on various event topologies for primary vertexing. And then we're going to have some conclusions and outlook. All right, so we don't need to go too much into this, but proton-proton collisions at the Large Hadron Collider. So as we all know, the LHC is an accelerator 100 meters below the surface. You know, it's the biggest proton-proton collider out there. So in all of this, what were we looking for in terms of why are we trying to solve this problem? Well, I was looking for a problem in high energy physics that has a natural formulation for quantum annealing and is simple. And the general motivation was to build expertise to formulate harder problems and more relevant problems like jet clustering or even high dimensional physics data clustering to find clustering is a sort of unsupervised learning, right? So you can look across your data space to see if there's any cluster of data that you previously did not look at. So we tried to find the simplest possible problem. And so the problem we chose was the problem of reconstructing proton-proton collision positions at the LHC. So the LHC, of course, circulates protons inside of beam pipes, not in a continuous stream, but in several closely packed bunches. And each bunch contains about 100 billion protons. And when they come together, they will collide maybe about 10 to 40 times. There will be about a few dozens of proton collisions at a given bunch crossing along one straight line. And so each of these proton collisions results in about 50 or more interesting tracks that are charged particles from that point. And so then the question is, which tracks came from which PP collision along that one-dimensional line, and where are these PP collisions in a given bunch? That's it. So that's the formulation of what primary vertexing is. Okay. So how do we do it? So well, we have the CMS detector as one of the 4 detectors at the LHC, which is, so the one I work with is the compact muon solenoid. And the charge part, so I have shown here where the protons come in from the two sides and then collides in the middle. and the charged particles are all reconstructed as tracks. And of course, when you reconstruct something as tracks, they come with their own uncertainties. And what we designate is where a track approaches the beam z-axis. So the z-axis I have shown in the picture there with me at the interaction point back in 2007. So along the z, you can find out where the track approached the beam axis the closest. And that is what we call the z of the track z naught. And along with that comes a delta z naught from the reconstruction uncertainty. So now the question is, so we try, so then the problem of finding the proton-proton collision points is reduces to a one-dimensional clustering problem. And that's what it is. So within CMS, we've solved it initially using simulated annealing, and I think the latest ones are using deterministic annealing. And this procedure is called primary vertexing. It's a fairly simple procedure. It's done offline, but it does have a lot of implications for multi-jet physics, and it can really enhance your physics if it's done well. So of course, it's annealing. So my question was, well, can it also be done with quantum annealing? And so it turned out it's a fairly easy problem to solve for quantum annealing, and we can actually solve it. Okay, so what is quantum annealing? Well, so quantum annealing has a history in the adiabatic theorem of quantum mechanics. And the theorem states that if a physical system, okay, let me just read this. A physical system remains in its instantaneous eigenstate through a slow perturbation in its Hamiltonian if there remains a gap between the eigenvalue and the rest of the spectrum. Okay, so if we start a system, as I've shown in the picture on the right, initially at the age initial, or the system is in the ground state, and then you perturb the Hamiltonian to some other Hamiltonian, so it has a different set of states, then the system will literally, it'll most probably end up in the minimum ground state of the new Hamiltonian. So how do you do computation with it? Well, you start with a simple Hamiltonian whose ground state is trivially reached, and then you perturb it into another Hamiltonian whose ground state is the solution to your problem. Okay, so this was, the people figured this out back in the 90s, I think. Now the only drawback on this is that the time you take to perturb your Hamiltonian from H initial to H final has to be at least greater than one divided by the inverse square of the minimum energy gap between the lowest eigenstate and the next to lowest eigenstate. And also experimental temperatures have to be kept less than this G-min by the Boltzmann constant. Okay, so this turns out to be technologically difficult to do, and so of course all of this means that the system has to be in quantum. You have to postpone decoherence beyond 1.g G-min square. So this is not this is not something that you can still achieve in the lab. So what people have done is they have used a slightly different paradigm. It's called quantum annealing. And this is basically going from the initial to the final Hamiltonian quickly and cleverly. Well, that is to say that there is a certain schedule in which you morph one Hamiltonian to another and repeat several times. And then you expect that the combination of quantum tunneling and thermal fluctuations will bring the system to the ground state. Now, the advantage you have is if you're very close to the ground state, but you are in a local minimum that is separated from the ground state with a large potential barrier. Well, then thermally, you would only get to them by e to the exponential of e to the power of minus delta E by kT, where delta E is the barrier height. Whereas quantum tunneling can get you to the ground state, it'll slide you into the ground state at square root of the height of the potential. So that is the advantage that you're looking for. And you repeat several times and exploit distribution. So that's the cartoon over there. So we're trying to use this. So D-Wave is a company in Canada that has commercial systems now. It was founded in 1999, and they originally was founded for gate computing, and then they eventually realized, well, gate computing is not the way to go for practical computing, and so then they focused on annealing. So I have pictures over there. That's what it looks like. They have a little chip at the end of a dilution refrigerator, and it's kept at, I didn't put the numbers here, it's kept at about 3 millikelvins. Okay, and so most of the cost is in the refrigeration. Okay, so what are the quantum bits, the qubits, made out of? The qubits are made out of radio frequency Josephson junctions, also known as quids, and they're niobium with aluminum oxide junction, and they operate at about radio frequency about 6 hertz. Okay, so there I have a schematic diagram of 2 qubits on the bottom right. And so they're basically the golden stuff. All three of the structures are qubits, but the 2 golden structures are the qubits that we're computing with, and the silver structure in the middle is a programmable mutual inductance between the qubits that is used to entangle the qubits together. So how this works is initially there's an external magnetic field or something like that is applied. They won't tell you the exact proprietary details of this hardware, but the general idea is we initialize all the qubits with a magnetic field in the x direction. And so this is implying that the computational basis is in the z direction. So if it's pointing along the z direction, the qubit is a 0. If it's pointing in the -1 direction, the magnetic field, it's 1, for example. So we start with the magnetic field in the x direction, and that initializes it to a Hadamard state, a 0 + 1, a superposition state. Okay, and then slowly we turn off this x direction magnetic field and turn on the problem Hamiltonian, which is in the z direction. Okay, and also the mutual inductances between the qubits, such that the ground state of this new mutual inductance and external magnetic fields is the solution to the problem you're looking for. So you can simply look at it. Well, on the left, there's an equation. It's just an Ising model, really. It's the sigma is the spins of the electrons, the h is the bias along the z direction, and Jij is the coupling between the spins. And so this can easily be represented again as a quadratic unconstrained binary optimization form, where Qi is just the qubit, which is 0 or 1, and A is just a real number, and Bij is also a real number, and Q and Qij. So it's a coupling, so it's a quadratic form. So any problem that can be expressed in the quadratic form could in principle be solved using D-Wave. So there's a few more hiccups on the D-Wave machine. Well, to stabilize qubits against thermal fluctuations, they induce strong couplings between physical qubits to establish a logical qubit. So on the left is a picture of how the physical qubits are connected to each other, and on the lines that have been shown, those are the couplings that are allowed. And the problem is always expressed in terms of logical qubits, and the D-Wave company itself gives you some embedding algorithms that take you from the physical graph to the logical graph you're looking for. Okay, so on the right, as I said, that the annealing proceeds by turning off one of the potentials, which is the A potential, and turning on the B potential, which is the problem Hamiltonian. Okay, so that's the whole thing. So the question next was, how quantum is a quantum annealer? And this is a hotly debated topic, but I think there have been some pretty well established evidence for tunneling in 2011 by the D-Wave people on the left, which was a letter to Nature. And there was a PRX recently in 2014 that does show that you can measure and actually establish Bell states in the quantum annealer. So definitely there is entanglement when we say coupling. All right, so let's get to the meat. How do we actually formulate this for the quantum annealer? Well, so let's say the tracks on the left, looking at the plot on the left, on the image on the left, well, there's a Z for all the tracks. And so let's see. So the probability that the ith track is said to have come from the kth position, collision position, is designated as PIK. And so in the diagram, it is PI0, and this is represented by a qubit. It's either 0 or it's 1. And then the coupling between two qubits, PIK and PJK, represent the association of these two tracks to the same collision vertex K. And that weight is the distance between these two track cuts, the Zi and the Zj, which means that this will be energetically unfavorable or punishing for associations between two widely separated tracks. And so this Dij is some measure of distance between these two Z cuts of the track. And so for now, we use the Manhattan distance, as just the absolute distance between the Zij, between Zi and the Zj of the tracks, normalized by the track uncertainties. And then finally, we have a function called the G of the Dij, which is basically an 1 minus an exponential, and this distorts the function that you put in there. And this distortion, it seems to us that it moves it unbunches or unsqueezes the eigenstates at the bottom of the well. Okay, so it kind of opens up the eigenstate. So then it definitively comes to the ground state when it does. And so this is just a distortion function. And of course, then there's also another final term which has a lambda. So you can think of it as a Lagrange multiplier, but it's really a penalty term. And this is enforcing that one track is only associated at most with one PP collision, or not just at most, it is associated with one PP collision. And so this lambda also was found by trial and error to be 1.2 times the maximum of the Dij. So that's it. So once the problem is formulated in this form, and you must remember Pik and Pjk are the qubits, and then those are the couplings, and so this can easily be turned into the Hamiltonian form. We can actually use it on our data. But of course, we didn't use it on CMS data because, it's hard to get to CMS reviews. So we generated artificial events. So we only used the published distributions from CMS, and we threw from these distributions. So on the left, so we threw from the known PP collision spectrum at P5 along the Z-axis. So we know it's a Gaussian about width of 35 millimeters. So we threw from there some primary vertices. And then from each of the PP collisions, we threw tracks based on realistic track reconstruction uncertainties, as have been published in our tracking paper, which is a Jinst paper. So we read this, the track etas and the track PTs, and we threw Monte Carlo, and we generate some tracks out there. So let's show the performance with one event. Okay, so on the left is it's a matrix. It's a lower triangular matrix, and this represents the biases and couplings between the logical qubits of the QPU as coefficients of the cuboform that was used to program the D-wave to solve a particular event with 3 primary vertices and 15 tracks, and where we know exactly what the Monte Carlo truth is. Okay, so when we apply it, when we program it onto the D-wave, the quantum state was prepared and annealed 10,000 times on the D-wave 2000Q2_1 CPU. And as you can see on the right, this is a distribution of the final energy spectrum. You can think of it as the eigenenergies of those. It's not really the eigenenergies, but it's the final solution energies you've come to. Okay, so this is a log plot. So the solution 1 is the ground state solution occurring at around 1.5 divided by Planck gigahertz. Okay, and so that is the best possible solution, and then there is solution number 2 are the next possible solutions, and then the solid lines are the valid energies where the lambda constraint is being respected, and there are some solutions in which the lambda constraint was not respected. So the result is that out of the 10,000 solutions, out of the 10,000 trials, 6,825 solutions are valid. So there's only one track associated with the one cluster, and of them 6,000. So then of those 6,615 solutions are correct with respect to what was entered in terms of the Monte Carlo truth. So we decided that the convergence efficiency for this algorithm is about 66%. And the small number of valid secondary solutions are typically where one track got misassociated with some other vertex that was not the originator of that track. So, okay, I have about 5 minutes left, so I'll go a little fast. So we try to benchmark this process against simulated annealing. So the first thing to recognize is that if we give infinite time to simulated annealing, it will always converge to the ground state, no matter how many false minima you have near the thing. You will always jump out of them and you come to the ground state. So when do we know when to stop simulated annealing? That is, how many iterations of simulated annealing is a fair comparison against quantum annealing. So there are two possible benchmarking approaches. One is to fix the efficiency for finding the correct solution. So for example, I found 66% efficiency for the quantum. So maybe we can try and see how much time does it take for a simulated annealer to get to 66% efficiency. But there are some drawbacks, because solution efficiencies are really distributions when you have a bunch of events, right? So then which solution efficiency do you match? How can you actually match the distributions? Also, it depends on event structure. So the other easy thing to do is to fix the time. So you allow the simulated annealing and the quantum annealing to operate on exactly the same amount of time and compare the true solution finding efficiency to get the right answer. And so this is easy to do. So then the question is, what are the relevant times for simulated annealing and quantum annealing? For quantum annealing is obviously the sampling time, and for simulated annealing is the CPU time spent on the number of sweeps that you're doing. So this has to be very carefully equalized between the CPU and the QPU fairly, and then compare the convergence efficiency. So quickly going on to how we measure the sampling time for the D wave. So the D wave sampling time, well, so on the diagram on the bottom right, I show that there is a big blue chunk of time that is required for programming the quantum processor. But once it is processed, you can set up the quantum system and then anneal it and then read out and then have a thermalization delay between them. So altogether, this process is repeated 10,000 times, and a single iteration of this process, which is called sampling, takes 164 microseconds on the D wave. Some of it is configurable and programmable, like the annealing time. Some of it is just hardware limited, like the 123 microseconds of the readout time. That can actually be improved according to the hardware designers at D wave, and that's purely classical. Okay. So the question is, how many simulated annealing sweeps can we fit into this 164 microseconds? Well, that depends on problem complexity. So next slide. So we try to write the most optimized simulated annealing algorithm we could make on a simple laptop, on a MacBook Pro. Okay, so the pseudocode of simulated annealing is fairly standard, you know. So in our case, the problem is expressed in cubo form for an array of n bits. Okay, and then we scan a temperature beta from beta initial to beta final. And how do we get this 0.1 and 10 is something in the backups, but we can talk about that. And then we sweep over the n bits within that for loop. And so when we arrive at each bit, we flip each bit and we measure the energy difference, if any. And if the energy difference is less than 0, we accept the new state of the string, of the bit string. If the energy is greater than 0, we accept the state with another probability of e to the power of minus beta times delta E. Okay. And so then we out of the for loop, we update the n bit array, and eventually outside it, we interpret the n bit array as a solution. So we also tried to speed it up as much as we possibly could. We used a sorted map where the keys are the bit indices and the values of the bits are the other bits that it's connected to and the coupling that it's connected to. So this requires us to only compute energy differences where there's a bit flip and not the whole thing. So that reduces the time per sweep from order n squared to order n. And also we use O2 optimization. It's purely C++. Everything is done directly on RAM, so it's really as fast as possible. So as you can see on the middle plot, different event topologies, like 2 vertices, 10 tracks. So that's a simple event topology that requires 20 bits to use. So that requires about 3.9 microseconds per sweep. So what we actually did is we measured the process time, not the wall time clearly. And then we processed and we measured the process time against the number of sweep, and we fit a straight line through it. So this discards any overheads in terms of programming. It really takes a slope. So the slope is the time per sweep. So for example, for 3 collisions, for 3 vertices, 15 tracks, we take 10.9 microseconds per sweep. Thus, we would say we could fit 15 sweeps into the 164 microseconds that D-Wave takes to solve a problem. So that is how we constrain our time. So so that is our way of constraining it. So coming to the final results. So this is the performance on 100 events.
Sorry to interrupt for a second. I just need you to wrap up in the next maybe 2 or 3 minutes.
Yes. Okay. So so we took 100 events with 3 PP-bar collisions and 15 tracks thrown from the measured CMS distributions. Each event was sampled 10,000 times. Yes. And so then on the left, we have a plot of the CPU distribution, the QPU distribution. They look kind of weird. So what we've tried to find is there underlying structure to this distribution? And yes, there is. So it turns out that depending on the intrinsic clumpiness of the event, the performance of the simulator on the quantum annealers differ. So to measure the clumpiness of the event, so an event that is highly clumped, where the different clusters have gotten merged, that has a low Dunn index. A Dunn index is defined on the left and it's on the right. So the increasing event clumpiness, increasing separateness among the vertices is on the right side of the Dunn index. And you can see that the CPU converges, has better and better efficiency as the vertices get nicely separated. And the QPU, the black dots, are kind of all over the place, but they're still rising. And we can discuss why these are all over the place. But let's go on. So the convergence efficiency increases with event clumpiness, and the QPU sort of beats CPU in efficiency for the same running time, but it's roughly similar. So then we tried over various different event topologies: 2 collisions, 10 tracks, 2 collisions, 16 tracks, 4 collisions, 12 tracks, 4 collisions, 16 tracks. And eventually, so the QPU seems to have advantage at low complexity. We're not sure why, but we are trying to understand this. So then finally, this is the money plot. So on the x-axis is the number of logical qubits, which corresponds to the complexity of the problem. And the black dots are the efficiency for solving it using the quantum, and the red dots are the efficiency for solving it using classical. And you can see there's a turnover point. Initially, the quantum is better, and then the classical turns over. But then certainly, finally, the conclusions. So the answer is the D-Wave quantum processor can reconstruct PP collisions at hadron colliders in limited capacity to only a certain number of vertices, beyond which it loses the power. But there's some intriguing quantum advantage for lower PP collisions and outlook. So we are beginning to seek more interesting clustering problems in 2D, 3D, and ND relevant for HEPX. So just to also let you know, this was our first attempt at using, our exploratory attempt at using D-Wave. So now we have developed sleeker algorithms to do clustering that can seed more sophisticated algorithms. We also have an acceleration program that is already very promising. So the graph embedding can be optimized to 2 times larger the problem size. Then there's ways to optimize the D-Wave mechanism itself by optimizing the annealing schedule for each physical qubit, and that offers a 10 to 100 times faster. And then there's also a problem, also a method called reverse annealing to intermittently scramble the Z information in the qubits. And this gives about 150 times better performance. And of course, we can also do hierarchical clustering for indefinitely large problems. And also at the bottom of all of this, the hardware itself is accelerating at Moore's law. And the next processor, which will have 5,000 qubits and 15 connections per qubit, is expected to be available mid-2020. So quantum annealing is about to kick off. And we hope to see if we can get some real HEPX problems onto quantum annealers and see how much better they do than other optimization problems. And of course, our paper is on archive, and you can take a look at it. We're going through peer review. We acknowledge support from the DOE and the Purdue Research Foundation. Thank you very much. Any questions?
All right, thank you very much. So we have maybe a very short time for 1 or 2 questions.
So, hi, Souvik. This is Maurice Garcia Severes. There are other annealers, not just other hardware annealers, right? Not just D-Wave, and not all of them quantum. Have you thought about running on other annealers?
Yes, in fact, the Fujitsu annealer is the next on our list. We're trying to, I've been emailing them to get us access, but to get that, I have to go through AWS. Then there's also the Toshiba annealer that they have. So we haven't. So the honest answer is we have not. But we have been funded for this summer to actually go ahead and try all these different annealers and see, where it's best.
I have a very, very quick question, just from my understanding. For the distance measure you're taking, it's one-dimensional to my mind, right? It's all in the C direction, so it's actually let's say, over-classification to call it Manhattan distance, right?
Yeah.
Yeah.
Well, it's just a distance.
So, yeah, I was a bit confused. I was a bit confused by that. Okay.
Yeah.
All
so
right.
eventually, more it should be a Pythagorean distance, and it should really for n-dimensional problems. Yeah.
One more quick question. I had one very naive, very quick question. You showed a lot of timing and so on, but do you actually find the vertices in both methods the same?
Yes.
Okay.
I mean, that was a big surprise that it actually worked. So, yeah, it was.
I just would have expected that you would have shown something like this to actually see that we see in both cases the or maybe I missed it, but
so
at
this
least
was
I couldn't
yeah.
Decipher this from the.
Yeah, that's right. I think I should have shown that, yes, these are the vertices point, like these are the positions of the vertices, and this is what the quantum annealer gives us back. But I think the best I did was on slide 11, where I showed the eigenstates. But yeah, okay, I just said, yeah, I didn't actually explicitly show it, but it does come back to the right answers.
Okay. All right, then thank you for the talk, and we can move to the next talk. Which I think is a short talk. I don't see it uploaded yet, but I see Jamie connected.
Yes, I'm here.
Perfect.
Oh, I cannot share actually. Maybe you can stop sharing. Sorry.
Yeah, Souvik, could you stop sharing, please?